All right, everyone, let's continue. We were still discussing what could happen to absorb energy, and we've seen basically thermal relaxation, we've seen fluorescence, and we've seen phosphorescence. Of course, the other basic interaction of light with tissue is scattering. So we can also represent that into the Jablonski diagram. In this case, as shown here. So now the dashed line, the virtual energy state, makes its appearance. So it's not a real energy state that is associated with the molecule, but somewhere in between. And the process here is that we have a photon of a certain energy, certain wavelength that excites the molecule to this virtual excited state, and then immediately there is a decay to the ground state again under emission of a photon. And since this, since now the energies of these two photons are the same, that also means that their wavelengths are the same. This process is called Rayleigh scattering or elastic Rayleigh scattering. It is the name elastic is because there's basically no energy transferred. There is only a photon very briefly interacting with the molecule and then remitted photon with the same energy, with the same wavelength. So basically, the only thing that happens from the point of view of the photon in this case is that its direction can be changed. There are some slightly more complicated forms of scattering interactions, namely Raman scattering. So again, we have now three Jablonski diagrams for three different processes. Rayleigh scattering is what I discussed on the previous slide, so that is just carried over from the other slide. Then we have Stokes-Raman scattering, where a photon excites the molecule to the virtual state, and then immediately a photon is emitted again. But this case, it is not. In this case, it is not emitted to the ground state, but to one of the higher vibrational states. So that means that in this case, the energy of the photon is just slightly less, and that the wavelength therefore is slightly longer than the excitation photon. Because again, every molecule has its own signature, so to say, of vibrational states. You can use this technique to probe these vibrational states of the molecule, because the energy difference between the excitation and the emitted photon corresponds exactly to one of these vibrational levels. So you can use this to probe the molecule. Then on the right-hand side is so-called anti-Stokes-Raman, where the molecule is excited from a high vibrational state of the ground state to a vibrational level, and then it decays back to the S0 state. So in this case, the energy of the emitted photon is slightly larger, which means that the wavelength is slightly shorter. But this process too, can be used to probe all these vibrational levels of the molecule. One quick question: it says in the slide that this anti-Stokes process is less likely than the Stokes-Raman. Can you imagine why this would be less likely? Ground state is the most common state. Yeah, that's exactly right. So it is much more uncommon to find. It's much more common to find the molecule in the ground state than to find it in a higher energy state where it has to be then already. So that just happens. It happens less. Yeah, that's true. All right, but now back to absorption. So let's say we want to use absorption for diagnosis, and here you can see two clinically important examples. The one is pulse oximetry, the thing for your finger. And the other one is a bilirubin meter, which is used in the neonatal clinic to measure bilirubin levels in newborns. Roughly, the approach is as always as follows. We measure a signal. Then from that signal, we try to extract the absorption coefficient or the absorption coefficient spectra. It depends a little bit on how many wavelengths we do the measurement, using some kind of theoretical signal model or description. So we model our signal first in the forward way. So what can we expect to measure when we have a certain absorption coefficient, and then for the actual measurement, we turn it around. We try to extract the absorption coefficient of the absorption coefficient spectra from that model. And then the last step is, if we have a quantitative measurement of these absorption spectra, is try to interpret that in terms of some physiological parameters. Normally, we don't care whether or not the absorption coefficient is at a certain number. We want to know whether the blood oxygenation level is sufficiently high, or we want to know if the bilirubin level is sufficiently low. So that the last translation step is also necessary. Okay. Then a question that we need to ask is, at what scale do we describe this absorption by tissue or by biological tissue? We can describe it as a function of the vasculature. So then we're looking at a larger piece of tissue. But, we could also describe the absorption properties of a single red blood cell, which would be a much smaller length scale. And we could even make it smaller. We could describe the absorption of a hemoglobin molecule. So it is important to keep in mind always at what scale that we're looking at. We're going to start at the molecular level, but we're going to scale it up later to the size of red blood cells, or the size of the vasculature. Okay, suppose we have a molecule and that is illuminated with light, which has an intensity given here by I0, and that intensity has units watt per square meter. So it tells you how much power is incident on the sample, or on the molecule in this case, per unit area. Now also suppose that, which is a little bit of a stretch for a molecule, but let's suppose that we can define a geometrical cross-section for that molecule. That would then have units of square meters. That allows us to calculate the incident power on the molecule. If we have I0 watts per square meter and we have a geometrical cross-section G of per meters, then the product of the two is the incident power on the molecule, P0. Now also assume that this molecule absorbs a certain amount of light, a certain amount of power. So we can also define the absorbed power as P sub A, P of A. And that allows us to define the first absorption property of this molecule, the so-called absorption efficiency, namely the ratio of the amount of absorbed power over the incident power, PA divided by P0. Yeah. Okay, I can go on. So we have P0, we have PA, we have the absorption efficiency. So we can combine these equations now as such. The absorbed power equals the absorption efficiency times the geometrical cross-section times the incident intensity. Agreed? You can work out the units for yourself, and then you'll see that it works. So we can now make a second definition, a second property, by combining the product of QA, so the product of the absorption efficiency Q and the geometrical cross-section G. If we combine that, the efficiency was dimensionless. The cross-section, geometrical cross-section, had units of square meter, so that means that this new absorption cross-section also has units per square meter. It's the efficiency times the geometrical cross-section. One way of one way of conceptualizing this absorption cross-section is more or less like it would be the kind of the effective area that the light is interacting with. If the absorption efficiency is very small, then only a small amount of light is absorbed, and it will be as if the light only sees a very small particle. If the absorption efficiency is very high, then a lot of light is absorbed, and it will be like the light sees the whole particle. All right. Well, since the amount of absorbed power always has to be less than the amount of incident light, that also means that the absorption cross-section is always going to be smaller or equal, at best equal, but smaller or equal to the geometrical cross-section. Yeah, great. Okay, then. So this was a pretty straightforward description introducing absorption efficiency and absorption coefficient for a single molecule. But now the question is, can we use this? Can we use this as well if we want to describe bonds of molecules, which is a much more realistic factor? And of course we can. So let's now take a bunch of molecules and put them in a cuvette, for example. Each of these molecules has an absorption cross-section sigma A, which equals the product, is equal to the product of the absorption efficiency and the geometrical cross-section, but we do assume that they are all identical. Then the power, that is the equation in the box on top of the slide, the power absorbed by only one molecule, A1, is then given by the absorption cross-section times the incident intensity. Now let's fill this cuvette with n molecules, n identical molecules, and let's say that the cuvette has a length L and an area that is illuminated A. So that means that these n identical molecules are all contained in a volume V is A times L. So the question is now, can we express the absorbed power by all these molecules, by all these n molecules, as a function of the incident intensity? Well, we can, because all these molecules were identical. That simply means that they act as if they would form one big absorber. So the total power absorbed by n of these molecules is simply equal to n times the power absorbed by the single molecule. So that just scales linearly. Or to put it in another way, the total absorption cross-section of this bunch of molecules, the total absorption cross-section equals the sum of the individual cross-sections of the molecules. Now we can relax, of course, we can now relax also the idea that all these molecules have to be completely identical. The last statement still holds. If you have a bunch of molecules, then the total absorption cross-section is the sum of the individual cross-sections in the cuvette. All right. So again, we have a cuvette with n molecules in a volume V that is given by an area A that is illuminated times a thickness of the cuvette, a length of the cuvette L. Now we define the density of the molecules. That is, for example, the number density. That is simply the number n divided by the volume in which they are contained. It has symbol rho. The definition is there, and it means that it has units of basically number of particles, number of molecules per cubic meter per volume. We also had that the total absorption cross-section was equal to the sum of the individual cross-sections. So we can write a sum that iterates over all the molecules in the volume. And in this case, when they were identical, we could just replace that with n times the cross-section of an individual molecule. And now we can define the final property, and we've seen that already before the break. We can define the absorption coefficient, or a little bit more formally, the density of total absorption cross-section. So we find that by taking the total absorption cross-section and dividing that by the volume that we're evaluating, and combining the equations on this slide, we see that n over v, n divided by v becomes rho, the molecular number density. So that means that we have a relation now between the absorption coefficient, symbol mu a, and the absorption cross-section of a single molecule, sigma a, and that is mu a is rho, the molecular density, times sigma a. All right, three absorption properties, efficiency and cross-section, are related to individual particles or individual molecules, and then the absorption coefficient describes the collective absorption by a number of molecules or a number of particles. Okay, there we go again. Same cuvette and molecules, same volume, and a given molecular density, number density. Now let's divide this cuvette that had length L. Let's divide that into small slices, each with a very small thickness delta L. Then it means that the number of molecules in each slice is going to be delta n, is going to be the density rho times the area A, that has not changed, times now the thickness of the slide, delta L. This is the number of molecules in each slide. Then we can calculate how much power is absorbed in such a slice, through such a slice. That will be delta P A is going to be equal to delta n, the number of molecules in the slice, times the cross-section, times the intensity at that point in the cuvette. That's why there is a functional dependence on E now. We can rearrange that a little bit and then have the equation on the right-hand side. So this is the absorbed power in one such small slice within the cuvette. Then we can calculate the change in intensity, delta E, when the light is passing through such a slice. So the slice of thickness delta L at location L, the change in intensity is given by the absorbed power, delta P, in units of watts, divided by the area, divided by A. So then we have, again, an intensity in watts per square meter. So this is the change of intensity when passing through that slice. Then we can calculate. Basically, we can calculate the intensity. That's the change in intensity. So we can write that as the difference between the intensity at the back of the slice and the intensity at the front of the slice. So that is the same. That is now on the left-hand side. On the right-hand side is still this change in intensity. And of course, you by now already feel that there is a differential equation coming, because if we now divide delta E, the change, by delta L, and make a delta L go to a really small number, then we end up with a differential equation. So again, this is the change in intensity as a function of delta L. So we can write that equation. The ideal is rho times sigma times E, and the solution of that is a simple exponential. You probably heard of it. You've probably seen it before. This is Lambert-Beer's law. So the intensity of the light as it passes through cuvette of thickness L is expressed as the input intensity on one side, I0, and then an exponential form, exponential minus the density times the cross-section, absorption cross-section of one molecule times the length L of the cuvette. The funny thing is they both contributed to this law. I'm not sure which one did which, but I guess let's say that Lambert was the one who found out that it should scale with the number density, and that Beer found out that it should scale with the length of the cuvette. So they both had some contribution to that law. All right. I have put on Canvas, and if everything is okay, it is on both of canvases of both courses. A small assignment, which I would like you to make. You can make it alone. You can make it in groups. That is all fine by me. It is the answer is also in there. So if you want to be a good sport, you will first read the couple of slides and then try to make the try to make the assignment, and then after that you can check if it works or not. So what I would like to try is just for you to see if you can do the assignment, and if everything is clear enough, you can use this the slides and the definitions that we just discussed. They're also on Canvas, and I'm curious what comes out. And of course, I'm still here. I'm going to stop the recording for now because that would be a little bit overkill.